Hi, this is Sai Potana, founder at Embedded Systems AI LLC. In this video, I'm going to walk you through RISC-V Boot Runtime Services Specification. Section 1 describes end-to-end boot flow to show the complete life cycle from power on to the application execution. When the system powers on, boot ROM performs minimal initialization and transfers control to platform firmware like SPL, U-Boot, or EDK2. Firmware initializes DRAM, CPU, devices, and then hands control to runtime services, which is nothing but an implementation of supervisor binary interface. These interfaces provide a standardized way to load operating systems and interact with them after they're loaded. Finally, user applications run on top of the OS. So the overall flow is power on, boot up firmware, activate runtime interfaces, boot up OS, and then launch applications. Section 2 describes boot runtime services architectural overview to show layered software architecture. First, let's picture the stack from top down. At the top, it's the application layer, the end user workloads, from user space programs to complex services. Below application layer, it's the OS layer, the kernel that schedules those user workloads, manages memory, and provides the core system services. After OS layer comes runtime services, the thin standardized layer that bridges the OS to the firmware, exposing a minimal portable set of primitives. After runtime services, it's platform firmware, the implementation specific code that configures the silicon, initializes devices, and enforces platform policies. The last layer is the hardware platform itself, the underlying silicon, which is RISC-V, peripherals, and interconnects that actually execute the instructions. Visually, you can think of these as concentric rings, each one trusting the layer beneath it while exposing a well-defined contract upward. Now that we have the stack, let's talk about the goals that drive its design. By standardizing the interface at the runtime services level, a single OS binary can run on any compliant RISC-V platform without source changes. Each boundary is defined by a stable versioned specification, eliminating vendor-specific handshakes. BRS deliberately mirrors proven ecosystems such as UEFI, ACPI, and SMBIOS, ensuring that tooling, management, and diagnostics work out of the box. The specification mandates a deterministic, cryptographically verifiable boot path from firmware to the OS, protecting the platform from tampering. So BRS defines the contract between the OS and the platform. That contract is the runtime service interface, the only thing the OS needs to know about the hardware. Everything else, device initialization, power management, security policies, remains hidden behind that contract. In Section 3, we'll walk through the three pillars that make the system work together seamlessly. First, the supervisor binary interface, or SBI, provides the essential runtime services that the operating system relies on. It abstracts the underlying hardware, presenting a clean, uniform API to the software stack. Think of it as the invisible bridge that lets the OS invoke low-level functions without worrying about the specifics of the chip. Next, we have the UEFI boot services. These are the tools that get the platform up and running before the OS even takes control. They include a boot manager that decides which image to run. They give us file system access during the early boot phase, allowing the firmware to read the configuration files and kernels. And crucially, they provide secure boot support, ensuring that only trusted code can start the system. The third pillar is the hardware description supplied to the firmware and the OS. This is delivered through ACPI tables, which describe power management, device enumeration, and system topology, complemented by SMBIOS tables, which expose detailed information about the platform's components like serial numbers, board revisions, etc. All of these pieces sit on a foundation of platform requirements that must be satisfied for the ecosystem to function correctly. These pieces are: first, a well-defined memory map that tells every component where it can read and write. The second piece is a clearly delineated privilege level, ensuring that only authorized code can perform sensitive operations. The third piece is precise reset and entry conditions, so the system can recover gracefully and start in a known state. In a single sentence, the BRS ecosystem combines runtime services, boot time capabilities, and comprehensive hardware description standards into a cohesive, secure, and portable platform. In section 4, let's dive into the supervisor binary interface and see how it bridges the operating system with the firmware. SBI is the OS to firmware interaction, the conduit through which the supervisor mode software talks to the low-level machine code that controls the hardware. From a functional standpoint, SBI offers a handful of essential services that the OS can invoke at runtime. Example services would be like timer services, inter-process interrupts, console I/O, system reset, power management, platform information. Now let's walk through a typical SBI call. The operating system running in supervisor privilege mode decides it needs a service, say a timer tick. So it issues an SBI request, passing the appropriate function identifier and any other arguments. The request lands in the firmware, which executes in the most privileged machine mode. The firmware translates the request into a concrete hardware action. Finally, the hardware carries out the operation, like starting a timer, sending an IPI, resetting the chip, and so on. Visually, you can picture it as a vertical chain: OS, SBI call, firmware, and then hardware. To sum it up, the key idea is that SBI is the runtime abstraction layer for the OS. It hides the raw hardware details behind a clean, uniform API, allowing the operating system to focus on higher level logic while the firmware handles the low level execution. In section 5, let's explore the UEFI boot services. It's a set of standardized mechanisms that takes a silicon platform from power on to a fully running operating system. From a high-level view, UEFI illustrates the standardized boot process. It gives every modern system a common vendor-agnostic way to initialize hardware, locate a boot image, and hand control over to the OS. UEFI bundles a rich feature set that the firmware exposes to the bootloader and briefly to the OS. It has a boot manager that decides which boot option to use, like a disk, network, or a USB, etc. Next, it has a driver model that loads and binds firmware drivers to devices, abstracting hardware details. It also has file system support, native access to FAT, exFAT, and other simple file systems, enabling the loader to read kernels directly from storage. There is also networking support, a pre-boot execution environment for network booting useful in data centers and thin client scenarios. UEFI also supports secure boot, a cryptographic verification of each boot component ensuring only trusted code runs. NVRAM variables are also part of UEFI. They are persistent storage variables for boot configuration, platform keys, and other firmware settings. Last but not the least, there is also a graphics output, a simple graphics output protocol that lets the firmware draw a splash screen or provide a frame buffer for early UI. Now let's walk through the UEFI boot flow step by step. Imagine the system just powered up. The first thing that happens is UEFI initialization. Firmware performs self-test, configures basic hardware, and builds the internal data structures. After that, there is driver dispatch. All built-in and optionally loaded drivers are enumerated and bound to the devices they manage. After driver dispatch, there is boot option selection. The boot manager consults the NVRAM boot order, evaluates priorities, and picks the next boot option. Then comes load OS loader. The selected boot option's loader image is read from the file system and placed into the memory. After all these steps, the boot services exit. At this point, the firmware leaves control of hardware resources like timers, interrupts, and memory. So, the OS can take exclusive ownership. And finally, the OS handoff. The firmware passes control to OS loader, which begins executing the kernel. Each of these stages is defined by the UEFI specification, which means any compliant firmware will behave the same way, regardless of the silicon vendor. UEFI provides an industry-standard boot experience by encapsulating boot time responsibilities like driver loading, secure verification, and handoff in a well-defined set of services. It eliminates proprietary boot code and gives OS developers a predictable, secure entry point. Section 6 describes the way modern computers tell their operating systems what they are made of through two critical standards, ACPI and SMBIOS. At its core, a hardware description is the conversation between the physical components of a computer and the software that runs on it. It answers the simple question, what am I dealing with? And it does so in a language the OS can understand. ACPI is the architecture for power and configuration. The Advanced Configuration and Power Interface, or ACPI, is a blueprint that tells the operating system how the machine is organized and how it should be managed. It has information about several hardware components like CPU topology. It tells OS how many cores, how many threads, and how many logical processors exist and how they are grouped. Memory layout. It discovers the physical address space, regions reserved for firmware, and where the RAM begins and starts. Device hierarchy. Every peripheral from the PCIe root complex down to the USB controller is placed in a tree that the OS can traverse. Power management. ACPI defines the states that lets the system throttle, sleep, or shut down gracefully. Interrupt routing. It maps which interrupt lines belong to which devices, enabling efficient, conflict-free signaling. In short, ACPI hands the OS a dynamic map of the machine and the rules for turning it on and off, and everything in between. SMBIOS is the system management BIOS, while ACPI focuses on runtime configuration, the system management BIOS provides static, descriptive data about the system itself. SM BIOS carries metadata for hardware components like system metadata, the make, model, and serial number of the chassis, manufacturer and firmware version, the vendor's identity, and the exact BIOS and UEFI revision running. CPU and memory configuration, a snapshot of the processor family, clock speeds, and installed DIMM sizes. SM BIOS is the identity card of the computer, giving the OS and management tools a reliable source of truth about the hardware's provenance. Armed with ACPI and SM BIOS data, the OS performs several tasks in a way which is hardware diagnostic. Discover devices automatically without manual driver installation. Match drivers to the exact hardware version, ensuring stability and performance. Manage power intelligently, extending battery life on laptops and reducing energy waste on servers. All of these actions happen behind the scenes, yet they are what make modern computers feel seamless. The essence of both standards is simple yet profound. They enable plug-and-play compatibility. By providing a common machine-readable description of the hardware, ACPI and SM BIOS allow any compliant operating system to boot, configure, and run without human intervention. Section 7 describes runtime services available after OS boot. Example services are like timer and timekeeping services, interrupt management, console debug output, power management, system reset, shutdown, firmware platform information, SBI extensions. All the runtime services have a stable ABI, supporting privilege separation and extensibility. Runtime services ensure continuous OS platform interaction. Section 8 describes device discovery and configuration to show how OS identifies and configures hardware. Firmware provides ACPI tables, SM BIOS tables, memory map, and I/O regions. OS actions include parsing tables, discovering devices, matching drivers, and configuring hardware. The result is a fully initialized system, so device discovery and configuration eliminates platform-specific OS hacks. Section 9 describes portability and ecosystem benefits to show why BRS is critical for RISC-V ecosystem. Benefits include same OS image across multiple platforms, reduced OS porting effort, industry standard alignment, improved security and reliability, support for servers, PCs, and embedded systems. As for ecosystem impact, it mandates hardware vendors follow BRS, OS vendors target BRS, tooling and firmware standardize, users get consistent experience. So to sum it up, BRS enables scalable RISC-V ecosystem growth. Section 10 shows complete BRS system stack. At the bottommost layer, it's hardware, and then comes firmware, which includes boot ROM, SPL, U-boot, EDK2, with standard interfaces like SBI, which is runtime, UEFI, which is used for booting. ACPI and SM BIOS describe the hardware. And then next comes operating system, which is Linux, BSD, or hypervisor. And the last layer is applications. So the outcome is a standardized environment with portable software stack and consistent execution model. The key idea here is BRS creates a unified platform software stack.